welcome to my presentation. My name is Lars Enghardt. I'm heading the Engine Acoustics department of the German Aerospace Center, and I will show you in the next 20 minutes some updates of our work on aeroacoustics. So this is me again, a little bit smaller, but don't worry, I will vanish in a few seconds. It's just to say goodbye for some minutes, and at the very end I will reappear and summarize what I've said in the last 20 minutes. Before I start with the content of our research work, a few words to my employer. The German Aerospace Center is the largest European research institution. It is publicly funded. It acts as space agency as well as project management agency. Our research area, you can see the different pictures here. From left to right, we are working on aeronautics, space research and technology, transport, energy, safety and security, and last but not least, digitalization. The German Aerospace Center has around about 9,300 employees working in 51 research institutes and facilities at 26 different sites spread all over Germany. As you can see on the map here, the red dots representing the sites of my institute, and the green spots are representing the different cities where our sites and institutes are situated. Moreover, we have external offices in Brussels, Paris, Tokyo, and Washington. So the Engine Acoustics department in Berlin is part of the Institute of Propulsion Technology, which is situated in Cologne and has affiliates in Göttingen as well as in Traun. The Engine Acoustics department, which I have the honor to head, has the following core competencies. We are dealing with turbo machinery sound sources, the engine core sound sources, jet noise, unsteady aerodynamics of the turbo machinery as a whole. So if we understand the sources, we go to the propagation. In the second row of this, so to speak, matrix, we see sound propagation in ducts, sound radiation, sound source localization, and sound absorption and liner. That's what we are also working on. And in the last row, we have active flow and noise control, acoustic pre-design, and of course we are operating experimental facilities, and we are using methods and tools. The first example of our research work I brought with me is a new test stand that we call CRAFT. CRAFT stands for Counter-Rotating Acoustic Fan Test Rig. The concept and setup of the new test rig is as follows. It is scaled, could be 1 to 2 or 1 to 3, 1/2, 1/3, and it's a highly flexible laboratory test rig with low operating costs for experimental investigations on aerodynamics and aeroacoustics. It is easily adjustable has a lot of different parameters that can be changed, like the actual distance between the rotors or between the rotor and the stator. It has, as you can see on the picture on the right hand side, a long cantilever hub, which is about 1.5 rotor diameters long. The rotor diameter is half a meter, so this cantilever is 1.5 meters long, roundabout. And this is useful for undisturbed aerodynamic and acoustic measurements behind the stage. The stage here on this picture is depicted without the shroud. So there is a shroud usually, and you will see this on the photograph in a second. We have three operating modes: counter-rotating, which is on this very picture here. So the first rotor rotates clockwise, the second rotor anti-clockwise. Then we have the flexibility to change into rotor-stator mode, where only the first rotor is rotating, and the second row is then not a rotor but a stator. And of course, two stages are also possible, where we have two rotors in a row and both turning in the same direction. Technical parameters. The shaft speed is up to 4,500 rotations per minute. The shaft power is provided by two electric motors. Each has capacity or power consumption of 25 kilowatts. The relative tip Mach number is 0.33, so it's rather low speed. The rotor diameter is, as I said, a little bit lower than half a meter, 45 centimeters roughly speaking. The tip clearance of the blades is 0.6 millimeters. And the Reynolds number that you can calculate by means of the blade tip, so the speed at the outer part or the upper part of the rotating tip, is 580,000. This is another graphical display of the whole setup. The flow is coming from the left, goes through a inlet control device, which I will show you a picture of in a minute, and then goes into the inlet, which we can equip with aerodynamic, with a lot of different aerodynamic and aeroacoustic measurement technique. Then we have the rotor, either one rotor or two rotors, the long cantilever hub, and then on the pressure side, a lot of different possibilities to have a measurement technique, and the whole setup is finalized in the very end with a throttle which changes the operating condition. Here you see the photographic impressions of the rig. On the left hand side, the picture shows the inlet control device, which is an in-house design and build. So it's still not 100% ready, but we are still working on it, but it should be ready for our first run, which will take place in 3 weeks' time. In the middle you see the picture of the whole setup with the inlet control device dismantled, unmounted, so you can see the inlet. And on the right hand side you see the rotor stator configuration installed, and this is the front view on the rotor. Research topics that we are dealing with, that we are planning to start in very near future, is firstly the influence of inlet distortions on fan noise. So we will place several means of inlet distortions in the front of the rotor, and then see how the acoustic and aerodynamic field will change. Secondly, we plan to do 3D shape optimizations for low noise design. This will be with the focus on tonal as well as broadband noise. And finally, the third idea we have so far in our head is rapid experimental validation of numerical tools. This is possible with this very flexible design here, where we can exchange rotors and stators quite quickly. Many other ideas are possible to be realized in this very setup here. So, and we are very happy to take this rig into service in the next months. The second example of our research work is a design to noise approach on fan noise. We are operating different means of the calculation of noise, analytical and numerical. This is a kind of cascade approach. So we start off with the very simple method we call 1D mean line method, where we take the input data, aerodynamic input data from the mean line. Just a few input values are necessary, and by means of an analytical approach we can perform trend studies. The second approach is a 2D through-flow approach, where the aerodynamic input data is taken from several flow streamlines. There we couple our aeroacoustic tool with the pre-designed tool of the sister department in the Institute of Propulsion Technology, which is called GTLab. We base our aeroacoustic and aerodynamic predictions on the pre-design of the engine. Then we have the 3D RANS mode, where we take the input data from stationary flow simulations. There it is possible to take into account realistic geometry and flow boundary conditions, and it is relatively low cost in comparison to unsteady or scale resolving simulation approaches. And last but not least, the method we call 4D harmonic balance, where we perform full numerical simulations of the whole sound field by means of a URANS approach, in using the harmonic balance method in our in-house DLR turbo machinery simulation called TRACE. By means of this technique, the tonal noise is calculated numerically, and this can be combined with our prediction tool, acoustic prediction tool called prop noise, to predict broadband noise as well. An example of such an approach to optimize an OGV, an outlet guide vane of a rotor stator stage, you can see here. The rotor is depicted here in front, just one blade, and here we have a quarter circle of the stator vanes, and you see the funny shape of the vanes which came out of the optimization tool. And these vanes from the numerical point of view are predicted to deliver a delta dB in comparison to classical vanes which are straight in radial direction. For two different operating points, for cutback and approach, CB and AP, this optimization was performed. And you see here for cutback in the numerical prediction tool says that it will deliver the change of the shape will deliver -3.8 dB and in the tones, and for approach it will deliver -8.5, which is really good. Not so good is that the other tool for the broadband noise simulation predicts a penalty for broadband noise. We get plus 2.1 dB for cutback and plus 1.7 dB for approach. Moreover, the efficiency goes down by 1%. But for tonal noise, this shape here, and this is just one of several different optimization results you can see here. The member 517 was chosen here, and this member has a very funny shape and delivers reduced tonal noise. The second example, which looks more reasonable, also reasonable to manufacture, is this here. There you have a quite straight shape in radial direction with a bend at the very end here, and this delivers not that much reduction in tonal noise, but delivers at the same time not that much penalty in broadband noise. You see that it looks much better to be manufactured, and the penalty on the efficiency is 0, so it should deliver the same performance as the classical straight OGV and produce less tonal noise. Another example of our research work is sound attenuation work on jet noise. The target of this approach here is a pressure control valve of a combustion test rig. As you can see here, it looks a bit like a cannon, but it's not. It's exactly a throttle which is connected to the outlet of test combustor of the test combustor exhaust pipe, and this device here controls the operating pressure of the combustor. It has a diameter of around about 1/2 meter here, and the central body, which is this yellow part here in this picture, slides actually in a profiled diverging section and can therefore change the diameter of which the flow passes so far, and so to speak, and by this it controls the operating pressure of the combustor, which is connected on this very side and can look quite differently. The jet exhausts, on the other hand, in this direction here, into the experimental facility, which is a big, huge room, directed in the facility and is afterwards directed in the facility chimney with a detuner. Depending on the operating pressure of the combustor, the excitation of jet noise can exceed 160 decibel, which is enormous. To reduce this high decibel value, we invented a pressure control valve for the combustor test rig. This is a 3D model, a small scale model. The scale is in the order of 1/20. The advantage of this is we can use a 3D printer to print a silencer prototype. This we do by means of stereolithography. It's an in-house realization, and the whole green part here is printed as one single part. And you see here on the left hand side, the gray part is a 1/20 model of the throttle that you saw in full scale on the last page. This is the lab where we tested the valve, as well as the throttle, as well as the pressure control valve, and last but not least the silencer. So we tested the new silencer for pressure control valves. Here you just see the model of the valve, and this is a pressurized tank which we can pressurize up to a certain limit. This sound meter measures the overall sound pressure level in this test room here, and on the next picture you see the result of this approach. The throttle noise is quite high and can get up to, depending on the outlet pressure level, can get up to certain limits. In this example here, up to 125 dBs. And if we install the silencer part, which is this part here, the throttle noise with silencer is reduced to a limit in the order of 90 dB, which delivers delta dB up to around about 26, 27, even 30 decibels are possible using this silencer. We are still developing on this model. We are planning to develop it further. We will change some parameters like the density of the holes here and change the shape slightly, and we plan to investigate half-scale model in the beginning of the next year, and at the end of the next year we would like to operate a full-scale model of this silencer. My last example of our research work is investigation on drone noise. There we are interested in the influence of the propeller blade counts of drones. The example here is a quadcopter, which you see a picture of on the right hand side here, on the perceived level of annoyance, because we sense that flying drones, they are quite annoying in a certain way. It looks a bit like a swarm of insects are flying, and we were thinking how and in what way we might change the overall appearance, acoustical appearance of these drones. And one idea is to change the propeller blade count. Not only the propeller blade count, also the propeller shape. And this we do by means of a design which is based on a quite simple approach. Then we 3D print the rotors. We check that the thrust is the expected thrust, which is meeting the requirements of the drone. Then we install the rotors. Here in this example you see the drone with one installed self-printed rotor here, and we do flight testing, and then we measure the sound. So what we are expecting to influence or have impact on the perceived noise levels is the number of blades. So we will change the number of blades of the self-printed rotors, so that we can expect a relative frequency shift. We might even change the number of blades of individual rotors, so that different rotors will get different blade counts. 2 blades, maybe then this can get 3 blades, this can get 4 blades, or even 5 blades, and the combination of all of them might sound not as annoying as the combination of 4 rotors having 2 blades each. So the number of blades can provide a relative frequency shift, and the speed variations of the drone controller of course leads to beat noise, and this is also changed when you change the individual number of blades. Moreover, of course, this is nothing we concentrate on now, but may be concentrating on in future, is to optimize the blade shape so that the source strengths will get down. This ends my little presentation. And as I said, I reappear. Thank you, Steve, for making this possible. Although it's virtual, it's better than nothing. So I think this is a good idea. I hope to see you all again in person and next year. Bye bye, and speak to you next week. So